first pre-recorded presentation by Jennifer Medina and Frederick Dauphin about wide field camera 3 infrared blob classification with machine learning.
What I'm going to be talking about is the supervised machine learning technique that we implemented in order to classify and detect these anomalies that are found in the wide field camera 3 infrared detector. They're called blobs. This is on behalf of the Deep WFC3, aka the WFC3 Machine Learning Working Group, here based on the Space Telescope Science Institute. So just to give a quick recap, the Wide Field Camera 3 is one of the instruments installed on the Hubble spacecraft. It has two different channels that you can observe through, the UVIS channel being available for UV and visible wavelengths, and the IR channel being available for infrared wavelengths. The topic that we're going to be discussing revolves around the IR channel. And depending on whether an observer wants to look through UVIS or IR, the flux gets redirected to either of the two channels using something called the channel select mechanism, and that's what we're going to be talking about today. So the blob anomalies, these are small particulates that are actually found on the wide field camera 3 channel select mechanism. And basically what these anomalies do is they block incoming flux from actually landing on the detector. So they manifest themselves as these little blob-shaped features of random size, and they're located in random spots on the IR camera. These are theorized to actually be pieces of cracked epoxy, this epoxy fluid that's basically holding the CSM together. And so the theory is that these pieces fall off of the hardware and into the CSM itself. And so that is basically what's blocking the incoming flux from bouncing off of the CSM and into the IR camera. So there's two reasons why it's critical to keep track of these blobs. The first one being that, as I mentioned before, because these pieces of cracked epoxy block light from actually landing on the camera, astronomers are potentially losing science pixels if these blobs aren't taken into account. And the second reason, which is the most important reason, is that because the theory is that these blobs are pieces of cracked epoxy, which is the material that's holding the CSM together, this might indicate that there's something going on with the hardware and that the CSM might actually be compromised. So the way that we monitor for the blobs is through our Quickbook API. There are a couple plots that we use to visually inspect and keep track that there are no new blobs that came into the picture. And these plots are shown on the far left and the far right of this slide. So the blob image is basically on the left, what I described before as being like a blob map. So it's just spatially showing you where all these blobs are located on the image. And the image on the right is the blob difference image. It basically will only show the new blob if there is a new blob. And this makes it a lot easier for visual inspection because if there is a new feature, it'll be the only thing in the frame. And as you can see, to make the blob difference image, you just take the current blob image and subtract by a median stack of the prior 30 blob images. And so the theory is that if a new blob does show up on the current blob image, all of the prior located blobs will be subtracted with the median stack. So the only thing that you should see in the blob difference image is the new artifact. So the theory is that we would take these blob difference images and feed it into the model. And the model's prior knowledge of what a blob looks like would allow it to determine whether or not there is a new blob located on the detector. if there's a new blob, it would automatically alert the wide field camera routine. And if there's no new blob, it would continue the routine the next day. So because we're using supervised machine learning, we're working with two different data sets labeled differently. So the label of 0 will indicate a subframe with no blobs, and a label of 1 will indicate at least one blob that's found on the subframe. So before going into how we made these subframes, I'll talk a little bit about the data preparation. So we use pretty standard practices for data preparation on the IR full frame images. The first thing we did was outlier clipping, where we replaced all of the outliers that land outside of 3 sigma with either the minimum or maximum pixel value thresholds that we determined for that image. And then the next thing we did was feature scaling, and the technique we used for scaling was Z-score normalization, which basically replaces all of the pixel values with the number of standard deviations they land away from the clipped mean. And that is pretty much all we do to full frame. To create the subframes, we first separate the full frame image between our training population and our validation population. So 75% of the image goes to training, the remaining 25% goes to validation. After we split up the full frame based on the training or validation, that is when we begin to diversify the data. And the first step that we do is we take random 256 by 256 cutouts or subframes of that region of the IR full frame. And for the blob images that are labeled 0, that's the point where we superimpose blobs that we generate from a randomly selected median stack from a single epic. The next thing we do for both the label 0 and label 1 data is we add noise and a normal distribution with a spread of 0.75. And then for spatial awareness, we randomly rotate the cutout and do some random flipping. And that is what you're looking at in the GIF at the bottom, is several examples of subframes and what they look like. So now I'll leave it to Fred to talk about the actual model architecture and the results that we got.
Thank you, Jenny, for introducing us to blobs and talking about our data prep. As she said, my name is Frederick Dauphin. I'm going to be talking about the model itself and then its results, and also going into some future work. So the model that we chose is called a convolutional neural network, also known as a CNN. And the reason we chose this is because it's very good at computer vision and recognizing patterns in images. We build our CNN using 2 convolutional blocks and then 2 additional fully connected layers. So in our first convolutional block, we have our input image being 2d6 by 2d6, and we trained 8 filters to create these feature maps. So we have our first convolution using ReLU as an activation function, and then also doing a 2x2 max pooling to go from 256 by 256 to 128 by 128. We then do another convolutional block. Instead of having 8 filters, we have 16 filters, and then also doing another 2x2 max pooling to go from 128 by 128 to 64 by 64. And finally, we have 2 fully connected layers. The first fully connected layer being 65,000 neurons from 1 pixel of each feature map being a neuron, and then the second layer being 128 neurons. And then finally, we have our 2 output neurons of 0 and 1 for our blobs and non-blobs. So these are our results as a confusion matrix. We're getting around 1% accuracy, which is pretty good. And confusion matrix tells us what our model is classifying correctly, what it's not classifying correctly. So in the top left, we have our model classifying non-blobs as non-blobs 88% of the time. And our bottom right, we have our model classifying blobs as blobs 94% of the time. The top right is our false positive, or our non-blobs being classified as blobs. And these are caused by this phenomenon called dips. So sometimes when we're taking our blob difference image, it's actually off by a pixel or 2. And instead of removing the blob, it's actually forming a shadow, and our model is classifying those as blobs. Our false negatives in the bottom left corner or our blob subframes being classified as non-blobs are images that are really just hard to classify. These should be images with a small blob, a faint blob, or a blob off the subframe. So to further motivate that our model is actually working, it's interested in blobs as a feature to use for classification, we use a method called Silency Maps. So look under the hood and figure out what our model is interested in. So Silency Maps will highlight the pixels that the model thinks it is extremely useful for classification. So on the left, we have an IR image around 2020, and it has one blob on it around 300 x-axis and then around 700 on the y-axis. And on the right, we have the Silency Map with a completely black background except for one lit blob in the middle, indicating that our model is interested in those pixels for classification. So for some future work, one of the caveats we want to address are Earth and city lights. These have a different background noise distribution than our images that we trained on. So we're interested in seeing if these images generalize and we're still able to find blobs on these Earth and city lights, or if we have to go back to the drawing board and retrain our model. In addition, we want to implement into AWS, so being able to utilize cloud computing in order to train deeper models and get better results. In addition, some of our next goals are identifying numerous anomalies in WFC3, since we have dozens of them, and then also being able to take it a step further and removing those anomalies and getting science pixels back. Finally, this project is in support of the institutional goal of incorporating machine learning and data science into astronomical processes. Within the next decade, using these are going to be extremely important for analysis, so it's better to get ahead of the curve. But thank you for joining our talk. In our top right, we have a QR code of our report if you're interested in further details, but we will be available for questions. So thank you for listening.
Thank you. Have we got the speakers available on the line to answer questions? Yes, yes, we do. So let me check the live questions channel for questions. I can't see any at the moment, so I'm going to take the liberty to ask one. Are there indications of likely or expected problems, arising in JWST imaging or spectra that you are considering, perhaps based on simulations and applications of your algorithms to those?
Sorry, could you just repeat that last part again, please?
Are you expecting similar or, well, unrelated problems that you could tackle with machine learning from JWST imaging?
Yeah, so that's kind of one of our bigger meta goals, is to work on these projects for HSC for future projects in preparation for James Webb, but also more specifically for Roman. I think one of the biggest challenges for Roman is the actual just pixel size. It's going to be around 300 megapixels, and doing traditional analysis on that many pixels and finding anomalies is just kind of out of the scope. So that's where machine learning can become extremely useful for doing those type of just super in-depth analysis that traditional methods wouldn't be able to handle.
So let's thank the speakers again, and let's move on to the next.